Okay, so hi everyone. My name is Adam Belay. I'm a professor at MIT, and today I wanted to give a forward-looking talk and talk a little bit about what might be possible in terms of benchmarking the cloud based on the capabilities and environment of the MOCA. So let's dive right into the motivation. So, of course, benchmarks are incredibly valuable, and it's because they set a target to aim for computer systems researchers. And so often in each subfield of computer systems, you'll start to accumulate a set of standard benchmarks, and over time, those benchmarks will be used as a basis for comparison for different systems in that particular area. And so that really encourages researchers to optimize for that set of benchmarks and to get the best possible performance. And I think David Patterson said it best, for better or for worse, benchmarks shape a field. And in particular, I'm concerned about the kind of negative connotation that's implied in this quote. And my specific concern is that benchmarks only really provide the most value when they can accurately capture the characteristics of production workloads. So that's what I'll be focusing on in this talk. So with that in mind, how good are today's cloud benchmarks? Well, this turns out to be a really hard question to answer because often the most interesting cloud workloads are proprietary or confidential, and so there can be a drift between the kind of benchmarks we're using to evaluate systems and the reality in the cloud. However, on a couple of instances, Google has compared what was going on from a tracing level in their large public clouds compared to some of the standard benchmarks that we're using in the computer systems community. And so I wanted to talk about that and just give a couple of examples of what we've seen so far. Okay, so one example that's really interesting is CPU performance. And here I'm summarizing the results of a paper from Google that was published at ISCA 15. So these are not my results, but I'm just summarizing Google's. And what was really interesting about this paper is they looked at spec CPU and other common CPU benchmarks, and then they compared those benchmarks to the types of CPU benchmarks we're using in the academic community to evaluate performance. And so this is a quote from the paper. The cloud performance was actually significantly different from the common wisdom for optimizing spec-like benchmarks. And the table on the left kind of summarizes what was happening here. So it's actually quite interesting. Most of the benchmarks we're using in the academic community are really well optimized. They have tight loops, very small amount of code, but real production workloads tend to be complex. They have lots of code. Much of that code is part of the active working set of the program. And as a result, it's hard for CPUs to actually cache those instructions. So just the raw working set size of the benchmarks of the real workloads is very large. And so in particular, this puts a lot of stress on the L2 instruction cache of the CPU at an architectural level. And it was actually 15 times higher than what we were seeing in spec. So that's an amazing difference. And what it means is that in the cloud, IPC, that's instructions per cycle, is actually universally low. In fact, it's usually below 1, which is like a pretty low number for a CPU. And so the implication here is that we really need to optimize for the front end of the CPU, the part that fetches the instructions, but that wasn't obvious as we look at these standard spec benchmarks. Okay, so I wanted to give you another example, too, of how benchmarks can be a mismatch from real workloads in the cloud. And this one is a much more recent study that looked at RPC overhead. This was at SOSP last year. And what's interesting here is, again, in the academic community, we tend to use benchmarks that really stress RPC performance, like Memcached and Redis and so on. However, in the paper, they found that latencies in real cloud applications are significantly higher than these benchmarks. And to give you some sense for how big of a difference this is, Memcached typical service time is about 1 microsecond. And on the other hand, in this study, they found that an average or typical service time was hundreds of microseconds to milliseconds. So that's an enormous difference. And I think what it means is that if we just go by these standard benchmarks, there's been a huge emphasis on supporting as many requests per second and making that as fast as possible. But actually, as it turns out, the optimizations we already have with technologies like kernel bypass are so fast already that we're getting up to the point where Amdahl's law is now in the way, and we actually can't yield better improvements for real cloud workloads. Now, on the other hand, this real data does reveal an opportunity, and that is that there's a huge amount of variability and dispersion in request service times. And so that means the emphasis shouldn't really be on how many requests per second, but rather how good are our congestion control policies and CPU scheduling algorithms and overload control algorithms so that we can cope with enormous differences in request durations. And that's what the graph on the left is showing. Okay, so clearly designing good benchmarks for the cloud is really hard. And if these two studies from Google are any indication, it seems like in many cases we're very far off from the benchmarks we use in the academic community versus the reality with real cloud workloads. So I think there are two reasons that make it really difficult to design good benchmarks for the cloud. One of those reasons is that workloads are rapidly evolving. So normally with benchmarks, you can have this process of iterative refinement where you design a benchmark, you can go to industry, you can get feedback, you can adjust it over time to make it more and more accurate. But in the cloud, the actual realities of these workloads are changing every year. And in fact, in Google's paper about CPU performance, they not only observed an enormous difference between standard benchmarks, but they also observed that that difference was shifting pretty quickly every year. So it's actually very hard to keep up with workloads in the cloud. The other thing that I think is really difficult is researchers often don't have access to either the hardware or software in a sufficient level of detail to really design great benchmarks. And so this is what brings us to the MOCA. I think we have an opportunity to actually cross out both of these limitations because the MOCA drives research and open source development on real hardware with real workloads. So this is a really exciting opportunity where we could rethink the way we design and deliver benchmarks for the cloud. Okay, so how can we actually go about doing this? Well, there's a lot of discussion yesterday about the idea of running research systems directly on the MOCA. And I think there's an enormous amount of benefit and value in doing something like this. However, I'd like to argue that this may not be the best approach for benchmarking specifically. And I have two main concerns. So one issue is that it's very hard to reproduce experiments across different runs when you're just running production work as it comes in, because there could be a lot of variability in that work. So that makes it harder to benchmark. And the other problem is that research systems are inherently experimental. So they may be less reliable than production systems, and we don't want to allow failures in research systems that we're testing to cause service outages or problems for other work that we're running in the cloud. Okay, so what could we do instead? Well, the proposal that I am offering in today's talk is this idea of packaging real workloads into benchmarks. And so specifically, I'd like to introduce this abstraction that I'm calling an executable trace. And an executable trace would capture and package all of the metadata needed to run real cloud workloads as benchmarks. Okay, so by having these executable traces, we can now run the workloads as many times as we need to, doing identical work each time, and that provides a basis for comparison across different potential research solutions that we're testing and evaluating. And so again, I think the MOCA is uniquely positioned to do something like this because it has access to real workloads, and also there's enough flexibility that we really could capture these traces in the real cloud infrastructure that's running the production workloads. Okay, so the obvious question then becomes, what kind of things should we capture? And I would like to offer three ideas. I think these are just some ideas among many that we could look at, but it may be interesting to look at serverless workloads and function as a service. We could look at DNN training jobs and DNN inference jobs. We could also look at web backends and capture data that's coming in through a load balancer. And the insight here is that for each domain that we might like to study, these are all domains that tend to have standard cloud computing benchmarks, the metadata that we actually need to record is a little bit different, and it requires us to hook into the system and record things in a different way. So let me give one specific example, in this case for function as a service, and I will use OpenWhisk, which is a popular open source platform for function as a service, just as an illustrative example. So in OpenWhisk, the structure of the system is pretty simple. You have a REST interface where requests come in. They go through a coordinator and through a reliable queue abstraction, and eventually they are delivered to invokers that run on each machine in the infrastructure, and those invokers run a series of containers that execute the serverless functions. Okay, so as these containers execute, they will complete their runs, and those completions will get stored in a distributed database, and that allows the coordinator to keep track of what work has been completed. So if we are going to turn this infrastructure into an executable trace, then we'd want to capture metadata at key places in the system. And so here's some thoughts on where those places might be. First of all, we'd want to be able to capture every request that's provided to the REST interface so we could replay it. We would also want to capture all of the containers. That's the entire image needed to run each program and the exact code and data that we're executing for each function. And then finally, not shown on this slide, we'd also want the raw input data sets that are fed to the serverless functions that they process. So if we could capture all of these things, then we could use them to build an executable trace, and that would allow us to replay that trace, and then we could remove OpenWhisk and replace it with any research system that we'd like to test and evaluate, giving it exactly the same inputs, and turning that load that the service was experiencing into a cloud benchmark. So that's the proposal here overall. Okay, so there are many interesting challenges in doing something like this, and this slide is only scratching the surface, but these are some of the things I've thought about so far. One challenge is just recording the data. So in particular, this is going to generate an enormous amount of metadata, and we don't want to slow down real production cloud workloads because we're trying to capture an executable trace for them. So I think this is a big engineering challenge. How can we record and capture metadata in a way that doesn't interfere with the real workloads that we're executing? Okay, and then another challenge is just the sheer large amount of storage that this will generate. We not only want to be able to store the data efficiently as the workload is running, but we also need to restore it quickly so that it's easy to run these experiments over and over again and try different approaches. And then on the workload side, there are also questions of which workloads should be included in the executable traces. And so it's probably the case that we don't want to record everything. And I could imagine a system where users of the MOC can opt in and volunteer the load that they're placing on the cloud and make it available to researchers so they can improve the efficiency of their systems. And so in this way, when workloads are not open source, or they're operating on proprietary things that haven't yet been published, then that could be excluded from these benchmarks. But on the other hand, users could choose to contribute their actual load and make that into a benchmark as well. And then finally, how can users actually run and execute the executable traces very quickly and very easily? One of the biggest challenges for great benchmarks is just how difficult it is for developers to use them. So how can we make it as turnkey as possible and require as little code and configuration for new research systems to play back an executable trace and apply that to their system to evaluate it? And maybe we could even imagine solutions where the performance evaluation and the measurement is actually part of the infrastructure that's provided to the researcher. Okay, so that's it for my talk. This is my proposal, and it'd be great to discuss it, and I'm happy to answer any questions.
I'm going to start with a question from the live stream. So Dwayne Branch is asking, so this FAAS would record metadata for data provenance and in federated learning, or would that be a different need?
Yeah, sorry, could you repeat the question?
Yep, so this FAAS would record metadata for data provenance and in federated learning, or is that a different need?
So I'm not quite sure if I understand the question, but to clarify, so for FAAS, I was referring to function as a service, and the goal here is to require all of the metadata you would need to perfectly replay the functions that are executing. So this is not related to a specific ML workload, although function as a service could be used as a platform to execute such a workload. Sure.
Yeah, so great talk. This is very interesting. I'm not sure if you were here yesterday for my talk about Memento.
I was.
It seems like, I mean, the architecture you had up for OpenWhisk, first of all, I didn't know about OpenWhisk. I'm definitely going to take a look. But there's this potential idea for collaboration. So what Memento is trying to do is almost like building on that question from the live stream and a little bit of an inverse of this. You know, Memento is trying to capture all the information that went into a computation, including the provenance, right? And so there's an extension of Memento called Memento Server, the idea being to do that whole thing as a functions as a service. And I can imagine in such a world that we have that kind of server that each of those invocations to a Memento function could then result in a potential package that you could use for benchmarking in the future. So I think this could be an interesting point of collaboration. No question, but I just wanted to sort of mention that we should link up.
Sounds great. Yeah. So what's really interesting is Memento and its metadata overlaps significantly with everything you would need to re-execute one of these workloads for a benchmark. So it'd be great to collaborate on this. And yeah, there's a tremendous amount of overlap. And in fact, the Mementos could be a really good benchmark in themselves because they capture so much of what's needed to perfectly recompute the previous job.
Hi, Adam. Thanks so much for the talk. I really think this is a great idea. And I think the idea of thinking about how to integrate this at a more systemic level in the MOC is really useful. Because, so that specific to the OpenWhisk example, so we did some of that work. And that's exactly what we had to do, right? So we created our own trace points. We then captured it. But we also did it so that we could either capture it at the TCP level and decide whether we wanted to include the network overheads or replay on the node itself. But to that point, I'm wondering whether there's a few things we can do here, right? So one, I think involving the switch infrastructure and potentially logging at points in the switch rather than introspecting on the code. And then the next thing that one might want to do, because I think even in our environment, it's not clear how many folks will do the opt-in or opt-out. So another option is that we build, we get the probabilities and we build distributions based on the trace, and then we generate the trace from those distributions, and that also takes care of some of the potential logging problems, right? Because we can build the distributions as the compression of the trace in the first place. But I think thinking hard about how we could deploy that, and maybe at that switch level, I think would be really cool.
Yeah, thank you for the comments. I agree that doing this at a switch level would be really cool because then you could just have an individual VM or container and replay back the network inputs into it, and that would allow you to benchmark and evaluate it at a different lower layer in the stack that's less of aware of the particular cloud programming model. So that's really cool, and that could be a good target point to look at too. Yeah.
Yeah, Shuan from Northeastern. Very exciting, ideas and interesting talk. So, I mean, two things I'm thinking is like, one is that, years ago, we were looking at stuff like with OpenStack, and it turns out like dependency hell is a really annoying problem, right? So it's gonna be a pain in the ass to reproduce the things without capturing all the dependencies. And then let's say you are using ROS projects and your libraries has dependencies of dependencies, you have a bunch of cargo logs. It's like that's like another side of the problem that you have to take care of. Otherwise, the reproducible problem is it's annoying. And the other thing is, I think for real, I mean, there's lots of cloud workload. There's Blueprint, there's Death Start, or whatever. I think for real cloud workload, one of the problems is something about the specific scenarios they run into, right? So like you said, the Google's workload, that's Google's case. Like if it go to Microsoft, Microsoft will be like, well, that's not true. Like we don't have that kind of problem. And I think it's gonna be like, how do you have those things like baked into the executable traces, but also some way to say like, you know what, this is like different things, and then like these things, you know, they're like, people, you don't want to take that too seriously, because then you perform very well on this workload and doesn't on that workload, doesn't make sense. Anyway, just some thoughts. It's, yeah.
Yeah, those are all really great points. So one thing that concerns me as well that overlaps with this is the workload characteristics of the MOC might be different from the workload characteristics of hyperscalers. But I think that's okay. I think if we can target real workloads that people are using and then orient our benchmarks to capture those behaviors, we're already moving in a step in the right direction where they're becoming more valuable. So that's one of the reasons I'm really excited about this.
It's just like, I think MOC would be a great starting point, right? So it would be interesting that Google says, well, we want to run these things here, and then see what that shows. So.
You were mentioning the effects of caching at the host level, but we have like 3 or 4 layers of stuff going on here, right? We have the hosts, we got the VMs, and then we got the Kubernetes on top of that. So which level of the benchmarks are you looking at? Are you looking at the Kubernetes benchmarks, or are you looking at the host benchmarks? And if you're looking at the Kubernetes, could you use the Jaeger trace facility to make these executable traces?
That's a great question, and I think it's something we have to figure out as a community. On a personal level, I'm interested in operating systems research. So a lot of the things I'd like to evaluate could be like seen as replacements or alternatives to Kubernetes or alternatives to the kernel. However, there are a lot of really exciting research projects that will also build on that infrastructure and may benefit from direct tracing from that level as well. So I think one of the big challenges is, can we support different levels of tracing and pick the right ones that are useful for a lot of different types of research?
Hi, great talk. I was just curious, it seems like there are lots of research questions around how do you even know that the workload that you're recording and the metadata reproduces the same results, right? And like I was just wondering if you had some thoughts on systematic ways to explore that, because it seems like that's just really cool.
That's a great question as well. So in a correctness sense, we could record and hash, just like was discussed yesterday, the output of the workload and verify that it produces the same answer, and that could help. But from a performance perspective, we may not always want it to reproduce the same result, because some of the layers we're replacing might impact how the network works or how multi-core scheduling happens and the order in which things run, and that could produce very big differences. And I think that's okay as long as the end-to-end performance improves. On the other hand, we may also want to study particular layers of the stack, like maybe we have a better congestion control algorithm and we just want to measure network congestion. That seems like a really important workload too. So balancing end-to-end versus studying specific layers seems like one of the big challenges in designing a solution like this.
Yeah, that's great. I was just wondering, like, do you need ground truth at the beginning, right? It's like you've reproduced the workload, you recorded it, and then it seems like you might want to be able to replay that in exactly the same system and try and get exactly the same results, and then be like, okay, we changed the scheduling order and all this other stuff, and we got better performance. So I guess I was asking about like that initial thing about recording.
That's a wonderful point as well. So a lot of real systems, including the Linux kernel, have this phenomenon called performance hysteresis, where you can run two different experiments with the same inputs and the same data and get very different performance results each time. And one actual research goal is building and designing systems that don't behave that way and are more consistent. So this presents a lot of challenges where you really need a lot of runs and a lot of statistical significance to draw conclusions. And that also is one of the challenges. Again, I think the experimental infrastructure that records and replays the execution traces might be able to help researchers with that by automating some of those difficulties. Okay,